Welcome to the course on error control coding and introduction to linear block codes. As we know, the error correcting and error detecting capability of error correcting codes depends on the distance profile of these codes. So today we are going to talk about the distance properties of linear block codes. We are going to describe what we mean by Hamming distance of codes, and then we are going to talk about how the minimum Hamming distance of a code is related to the columns of a parity check matrix. I am first going to describe what is Hamming weight. So, if we have a n tuple, let us call it V. So, V is an n tuple, and since we are restricting our discussion to binary linear block code, so we consider a binary n tuple. So, this V0, V1, V2, Vn minus 1 could be either 0 or 1. So, we define the Hamming weight of this vector V as number of non-zero components of V. So, for example, let us say V is 0, 0, 1, 0, 1, 1. Let us say this is my V. So, we can see here how many non-zero components we have, 1, 2, 3. So, the Hamming weight of V is, in this example, 3. Now, let V and W are two n tuples. So, we define the Hamming distance between V and W, which is denoted by dVW, as the number of places where V and W are differing. So, for example, if V is given by this 1 0 0, 1 0 1 1, and W is given by 0 1 0, 0 0 1 1, then what is the Hamming distance? Let us look at the first location. This is 1 and this is 0. So, they are differing in the first location. So, that is 1. Similarly, the second location, this is 0, this is 1. So, they are differing. So, now its Hamming weight is Hamming distance 2, 0 0, both are same. The third bit location, fourth bit location, this is 1 and this is 0. So, they are differing. So, Hamming distance is now 3, 0 0, they are same. This bit location, both the V and W are 1. Similarly, in this location, V and W are same. So, that means our Hamming distance between V and W is 3, and these are the 3 locations where they are differing. One is this first bit location, second bit location, and this fourth bit location. So, the Hamming distance between V and W in this example is 3. Now, if V, W, X are 3 binary n tuples, then the Hamming distance between V and W, Hamming distance between W and X, and Hamming distance between V and X satisfies this inequality, which is known as triangle inequality. So, what is triangle inequality? The Hamming distance between V and W plus the Hamming distance between W and X is greater than equal to Hamming distance between V and X. So, let us first try to prove this triangular inequality. So, let V, W and X are 3 binary n tuples. So, the Hamming distance between V and W can be defined as Hamming weight of V plus W. Note that we are talking about binary n tuples, right? And what is Hamming distance? Hamming distance is number of positions in which V and W are differing. And since we are talking about binary n tuples. So, the number of places where V and W are differing can be found if we add V and W, this modulo 2 addition of V and W, and we find out the positions where the sum is 1, because only in those locations where these bits are differing, V plus W will be 1, otherwise it will be 0, because we know for binary modulo 2 addition 0 plus 0 is going to be 0, 1 plus 1 is going to be 0, only when they are differing 0 plus 1, in this case it is going to be 1, and if this is 1 and this is 0, in this case also this Hamming weight is going to be 1. So, we can write down the Hamming distance between V and W as the Hamming weight between V plus W. Similarly, we can write the Hamming distance between W and X as the weight of this vector W plus X, and we can define the Hamming distance between V and X as the weight of V plus X. So, if we have two code vectors A and B, we know the weight of A plus weight of B is going to be greater than equal to weight of A plus V. Only when the ones in A and B are non-overlapping, this is going to be equal, otherwise weight of A plus weight of B will be greater than weight of A plus B. Now, let us choose our A and B wisely. So, let us choose A to be V plus W and B to be W plus X. If we choose these values of A and B and put it in this inequality, what we get is weight of V plus W plus weight of W plus X is greater than equal to weight of V plus W plus X. W plus W is going to be 0. So, this will be V plus X, this is given by weight of V plus X. So, what we have shown is weight of V plus W plus weight of W plus X is greater than equal to Hamming weight of V plus X, and weight of V plus W is nothing but Hamming distance between V and W. So, this we can replace by Hamming distance between V and W, this we can replace by Hamming distance between W and X, and this we can replace by Hamming distance between V and X. Hence, we get the Hamming distance between V and W plus Hamming distance W and X is greater than equal to Hamming distance between V and X. Now, let us define what do we mean by minimum distance of a linear block code. So, we define a minimum distance of a linear block code in this fashion. It is the minimum Hamming distance between any two code words. So, we define minimum distance of a linear block code C as minimum Hamming distance between V and W, where V and W are code words and V is obviously not equal to W. Now, this can be written as, we will come to that. Similarly, we will define a minimum weight of a code. A minimum weight of a code is defined as minimum Hamming weight of code V, non-zero code word V belonging to this linear block code C. It is easy to show that the minimum distance of a code is nothing but minimum weight code word of a linear block code, minimum weight non-zero code word. So, let us see how we can show this. So, minimum distance of a code is defined as minimum Hamming distance between any two code words V and W belonging to this linear block code C, where V is not same as W. Now, we know that Hamming distance between V and W can be written in terms of Hamming weight of V plus W. So, this can be written as Hamming weight of V plus W. So, we can write minimum distance as minimum Hamming weight of V plus W, where V plus W are code words belonging to this linear block code and V is not same as W. Now, V plus W, V plus, since we are talking about linear block codes, sum of two code words is also a valid code word. So, V plus X, V plus W is going to be another valid code word belonging to this linear block code C. So, we can write this as minimum weight of a code word X belonging to this linear block code, where X is a non-zero code word. So, in other words, this is then nothing but minimum weight of linear block code C. So, we can write then minimum distance of a linear block code to be equal to the minimum weight of a non-zero code word belonging to C. Next, we are going to show how is minimum distance of a linear block code related to columns of a parity check matrix, and how from the columns from the parity check matrix we can find out what is the minimum distance of a linear block code. So, the result which I am going to show you is as follows. If C is an nk linear block code whose parity check matrix is given by H. So, for each code word of Hamming weight L, there exist L columns of this parity check matrix H, such that the vector sum of these columns is equal to 0 vector. So, let us prove this. Let us say we can write the parity check matrix in this form. Note, this is n minus k cross n matrix. So, there are n columns which we are denoting by H0, H1, H2 and Hn minus 1. So, Hi represent ith column of this parity check matrix, and we said that for each code word of Hamming weight L. So, let us say that at this location I1, I2, I3, IL, these are the locations where the code word is basically has a non-zero weight. So, let the non-zero components of this code word V be denoted by Vi1, Vi2, Vi3 and VIL, where we just without loss of generality we are just writing them as I1 is less than equal to I2 is less than equal to I3 is less than equal to IL is less than equal to n minus 1. And since these are the non-zero components of the code word, so at this location V will be 1, at other locations where there are 0 components, the values of V at those locations will be 0. Now, we know that if V is a valid code word, then VH transpose is equal to 0. So, if V is a valid code word, then VH transpose is going to be 0. This we can write as V naught times H0 plus V1 times H1 plus V2 times H2 plus Vn minus 1 H n minus 1. Now, note that among these V0, V1, V2, Vn minus 1, there are L components which are non-zero, and what are those L components? Vi1, Vi2, Vi3 up to VIL. So, all other components of V will be 0. So, here then only terms that will be left, we are left with is basically this Vi1, Hi1 plus Vi2, Hi2 plus up to VIL HIL. Now, since VI1, VI2, VI3, VIL is 1, we can write this as HI1 plus HI2 plus HI3 up to HIL is going to be 0. And what are these HI1, HI2, HI3? These are columns of your parity check matrix H. So, what does this say? It says that if we do vector sum of these L columns of parity check matrix, then basically their vector sum is 0, and that is what the theorem is about, that if there exists a code word for each code word of Hamming weight L, there exist L columns of parity check matrix whose vector sum is equal to L. So, we showed that if L components of this code word V are non-zero, then this relation follows. Next, we show another result which says if there exist L columns of parity check matrix whose vector sum is 0 vector, then there exists a code word of Hamming weight L in this linear block code C. So, let us see. So, suppose these L columns of parity check matrix H whose vector sum is 0 are given by HI1, HI2, HI3 up to HIL. Then what we have is HI1 plus HI2 plus HI3 up to HIL is going to be 0. Now, let us consider an n tuple, we denote it by x, whose non-zero components are given by xi1, xi2 up to xil. In other words, at L locations, this n tuple is non-zero. So, the Hamming weight of x is L. Now, we want to show that if there exist L columns of this parity check matrix H whose vector sum is 0, then there exists a code word whose Hamming weight is L. So, next we are going to show that if this condition happens and if there is an n tuple whose Hamming weight is L, then this x has to be a code word. So, how do we show x is a code word? Well, if x is a code word, x h transpose will be 0. So, let us evaluate x h transpose. So, what is x h transpose? It is given by x0 h0 plus x1 h1 plus x2 h2 plus up to xn minus 1 hn minus 1. Now, since we know that L elements of these n tuple x are non-zero and they are given by xi1, xi2, xi3, xin L. So, then we can write this as xi1 hi1 plus xi2 hi2 up to xil hil. Now, since xi1, xi2, xi3, xil they are all 1, we can write this as hi1 plus hi2 plus hi3 plus hil. Now, what did we say about vector sum of these L columns? We said the vector sum of these L columns is 0. If that is the case, then this is equal to 0. So, what we have shown now is x h transpose is 0. Now, if x h transpose is 0, then x has to be a valid code word. So, we have shown that if vector sum of L columns of parity check matrix H sum up to 0, then there exists a code word of Hamming weight L. Now, using these two theorems, this theorem and this theorem, we can make these following observations. If C is a linear block code with parity check matrix given by H, and if no D minus 1 or fewer columns of parity check matrix add up to 0, then the code has a minimum weight of at least D. So, minimum distance of code is at least D if no D minus 1 columns of this H matrix, the vector sum of these D minus 1 columns or fewer columns of these H matrix, if they do not add up to 0, it means the linear block code has at least minimum distance of D. The second statement that we can make is, if there is a linear block code C with parity check matrix H, then the minimum weight of this linear block code C, D min, is basically equal to the smallest number of columns of this H matrix whose vector sum add up to 0. Thank you.